This is an introduction to approximation algorithms by the example of the greedy algorithm for vertex cover. So why are we interested in approximation algorithms? There are many hard, NP-hard problems, in particular NP-hard optimization problems, like the traveling salesperson problem, like maximum satisfiability. You're wondering, why don't I say simply satisfiability, but maximum satisfiability? Because we're here interested in the optimization problem, not the decision problem. So there are many NP-hard optimization problems, and an optimal solution for us is out of reach, particularly assuming that P is not equal to NP. However, in many cases, we can find good approximations. So that's what we want to do. And we want to learn about techniques to design approximation algorithms. And we do so by the example of specific problems. So the technique, if you want to call it this, that we're going to look at today is lower bounding the optimal solution. So lower bounding the optimal solution is key to approximation algorithms, as we will also see today. And the problem that we're going to look at today is vertex cover. So let's look at vertex cover. We have as input a graph, and we want to compute a minimum vertex cover. What does that mean? We want to compute a subset of the vertices that cover all edges, in the sense that for every edge, at least one of the endpoints is in the set. This is a vertex cover. Let's do that. So if I add this vertex to the set, then I have two edges covered. Maybe this one covers two more. This one covers one more. It also covers one that we already had, but that doesn't help. Now two more. This one covers one more. This one covers two. Now the colored vertices would be a vertex cover. But what we're interested in is not any vertex cover, but a minimum vertex cover. So a vertex cover that is as small as possible. So we now have a vertex cover. Natural question, is it optimal? So is it a minimum vertex cover? Obviously it isn't. You can easily drop the point on the left. The two edges are actually still covered. We can also easily drop the point at the top right. Those edges were also previously covered. Same is true for the pink one. Now for this vertex cover, we can still ask, is it optimal? So let's see. Assuming it's optimal, can we somehow argue that it's optimal? Here's a simple argument, but which will be useful also later, and that is the following. Look at the following four edges. And let me highlight them once more. Here's 1, 2, 3. Of course, these edges, being part of my overall edge set, have to be covered by a vertex cover, in particular by the minimum vertex cover. But as you see, these edges do not share any vertices. So it's a so-called matching. Since they do not share vertices, a vertex that helps me cover, let's say, the edge on the top right. So this edge, maybe this vertex here, it's actually only that one or the other endpoint, will not help with the other edges. So for each of these edges, I will need to pick one of its endpoints into the vertex cover. So 4 is optimum here. In this example, that was not too difficult, but generally this is an NP-hard problem. So there's no hope that we can give an efficient algorithm that solves this problem efficiently in general. We can still think about exact algorithms. So there is a simple exact algorithm. We can simply test all subsets of vertices. If I have n vertices, I have 2 to the n subsets. For each subset, I can see whether, for each of the edges, whether it's covered. So that gives me a running time of 2 to the n times m. Noteworthy alternatives would be I can formulate this as an ILP and use an ILP solver. So if I really want to have an exact solution, that is a good option. This is also a problem that has been extensively studied in parameterized algorithms. So assuming that a graph has a vertex cover that is not too large, so let's say I'm looking for a vertex cover of size k, then I can actually give an efficient solution in terms of the graph size. But more about that when we do parameterized algorithms. But what we're going to look at today is not finding the exact minimum, but trying to approximate it. And let's say I find a solution like this one with 5 vertices, and actually in terms of its quality, it's not too bad, because 4 is the best I could get. 5 is what, in this example, I would have. So 5 over 4 is a reasonable approximation ratio, not a one that we can actually achieve. And this is just for this example. Before looking at an approximation algorithm for vertex cover, let's first review some key concepts. And the first concept is an NP optimization problem. An NP optimization problem is given by a set of instances. And for each instance, we have a set of feasible solutions with the following properties. So first of all, we want to be able to bound the size of the solution in terms of the size of the instance. And then we want to, for a given S and an instance, be able to, in polynomial time, check whether S is actually a feasible solution to I. So we also want to have an objective function, which for any solution to an instance gives me a value, a non-negative value, and we want to be able to also compute this in polynomial time. And we're going to look at either minimization or maximization. So let's look at this by the example of vertex cover. What is the set of instances? Instances are the inputs. So the input to the vertex cover problem is a graph. So this set is a set of graphs, and an instance is a specific graph G with vertex and edge set. Given this instance, so what is its size? The size of a graph is number of vertices plus number of edges. And what are the feasible solutions? So the feasible solutions are simply the set of all vertex covers of this given graph. Now we want to argue that the size of the solution is polynomially bounded by the size of the instance. So a solution is simply a subset of the set of vertices that obviously is bounded by the instance size, which is vertices plus edges. Now additionally, we want to be able to efficiently decide whether the solution is actually feasible. If I have a solution, I can very easily go through the set of edges and check whether it is actually a vertex cover. So also that we can do. Now the objective of a solution, the objective function of a solution is quite simple. We simply want to minimize the size of the solution, and that can be easily computed. And of course, we have a minimization problem. So we want to compute a vertex cover that is as small as possible. So that's an NP optimization problem. Let's look at the case of a minimization problem. For a feasible solution, we say it's optimal if the objective function on the solution is minimal among all objective values that feasible solutions achieve for this instance. Same for maximization problem, obviously we want to have maximum. And the optimal value of the objective function we then denote by opt. Or if we want to give also the problem and the instance, we additionally give that, but typically from the context that's clear, and then we just say opt, and that's the value of the objective function for an optimal solution. And now we can define what an approximation algorithm is. So for a minimization problem and a given rational alpha, a factor alpha approximation is an efficient algorithm. So efficient means polynomial time, such that for any instance, it computes a feasible solution with a property that the objective function of that solution compared to the optimal objective function, so the objective functions of the optimal solution, so the minimum one, is at most alpha. Often you will see this also as the objective function of the solution is bounded by alpha times the optimum. Now, sometimes we want to express the approximation factor as a function of n. In that case, alpha is a function from the natural numbers to the rationals. And then here also I have an alpha of input size. An example for this, which we will see for set cover, is that there we get an approximation factor of O of log n. Not a constant, but something depending on n. And then for maximization problem, we get larger. Now with all the concepts in place, we can give an approximation algorithm for vertex cover. Before we look at a solution, I think it's a good idea for you to think about how would you compute a vertex cover. And I think a natural strategy is greedy, either edge-based, so you're trying to make sure that you cover every edge, or vertex-based, where you start adding vertices. You could also think of strategies where you start with all vertices, start removing ones. But let's look at vertex. And let's do something very simple. I just add vertices one by one and remove the edges that are covered. So if we do not do anything clever here, then this could go badly wrong. So let's take this graph. If I just take an arbitrary vertex, this one here, then okay, that edge is covered. Then I take that one, that one, that one, that one, that one. So if I never decide to pick the middle one, this can get arbitrary bound. Of course, when you do vertex by vertex, you can come up with better strategies like picking the one with the largest degree. When we talk about set cover, then we will also talk about this strategy again. But for now, we will look at a different option. But before doing so, we have to think about the following. If, no matter which strategy I have, I want to say something about the quality, then I have to bound the objective function that I get in terms of the optimum value for the objective function. But that's difficult since computing the optimum is difficult. And now comes the key ingredient. Instead of comparing to the optimum, we are going to compare to a good lower bound. So a lower bound, which hopefully is fairly close to the optimum. And our approximate solution, we then simply compare to this lower bound instead. Because if I want to bound the objective function of my algorithm divided by opt, I can bound this by the objective function divided by the lower bound. So how can we give a lower bound on the size of a vertex cover? Now we come back to the example that I had previously. Here we said the optimum is 4, and we could see this because all of these edges, so those 4 edges, needed to be covered. So we need at least one vertex for each of these edges. And this points at a lower bound based on matching. So what we have here is a so-called matching. The matching is a set of edges in a graph, so that there are no two adjacent edges. Stated differently, they do not share any vertices. So this is a matching. It's not a maximal and it's not a maximum matching. What we're going to look at is maximal matching, so they don't have to have maximum size, but we want to have matchings where it's not possible to add any more edges. So this here is a maximal matching, because no matter which edge I would try to add, like this one, I already have that endpoint here covered. So that's not possible. No matter which matching we have, but in particular for maximal matchings, the optimal will have to be at least the size of this match, because I need a vertex cover which at least also covers these edges. Now you might wonder, is it the same computing a maximum matching and computing a minimum vertex cover? So that's not the case. So for instance here, odd length cycle, maximum matching has size 2, minimum vertex cover has size 3. So that's not true, but we have the matching as a lower bound. Now, given a matching, can we come up with a vertex cover? And this vertex cover, as a hint, will have size 2 times the size of the matching. What we can do is simply for each of the edges in the matching, take both endpoints. Assuming this is a maximal matching, so we have to take a maximal matching, but assuming this is a maximal matching, every edge is covered. Why is that the case? Assume there's an edge that is not covered. That means that both endpoints are not incident to any of the vertices of the matching edges, so something like this. But this means that we could have actually added this edge to our matching. So the matching was not maximal. If you have a maximal matching, then taking both endpoints for each of the edges in the matching gives me a vertex cover. And that's our algorithm. Computer maximal matching, take both endpoints of each of the edges. Done. Now if you ask yourself how well this algorithm performs, so the solution to this algorithm gives me something that has twice the size of the matching. But now we have for any matching that the optimum is at least as large as a matching. Plugging this in here, I get that the algorithm, the solution that the algorithm is bounded by 2 times the optimal solution. So we have a 2 approximation. Here once more the algorithm. It's really simple. We start with an empty set of matching edges. We go through all of the edges. If it's not adjacent yet to any of the edges in the matching, we simply add it. And then we return the set of endpoints of the edges in the matching. This gives us a true approximation. Now, in the design of approximation algorithm, we at this point should ask us a couple of questions. And here they are. So first of all, we have now proven that this algorithm is a true approximation, but maybe it's even better. So that's question number 1. Is there a better analysis for the given algorithm? Next question is, given what the lower bound gives us, could we design a better algorithm using that lower bound? Question number 3 is there actually a better lower bound for designing an approximation algorithm? Let's look at these questions one by one. And to answer the question whether there's a better analysis, we should first see whether this factor 2 is tight in our case. And it is. So it's easy to give examples. One example is the following. If I have a complete bipartite graph, so I have n vertices here, n vertices here, and between every vertex on the left, every vertex on the right, an edge, then a maximal matching would be, for instance, this one, where for every vertex here I connected to a vertex there. The matching has size n, the vertex cover has size 2n. But an optimal vertex cover simply picks vertices from one of the sides, which is n, meaning that in this example, the approximation factor that we get is actually exactly 2. Now the next question is about, can we use the size of a matching to get better approximation algorithms? And for that, we want to look at the size of a maximum matching versus the optimum and how far those can be apart. But if they can be a factor 2 apart, then we can also not hope to get anything better from this lower bound. And that is indeed the case. So if you take the complete graph on n vertices, the maximum matching, when n is odd, will have size n minus 1 half. Because I can essentially pair up the vertices, one will stay, since n was odd. In contrast, a minimal vertex cover will have size n minus 1. Why is that the case? Assume you would have a vertex cover of size n minus 2, then there are at least 2 vertices not included, but there's an edge between those 2 vertices, and that's not covered. But now you see there's a gap of a factor of 2 between those. And what that means is that this lower bound on the number of matchings will not help us to get anything better than a factor of 2. Now the final question is, are there other ways to design better approximation algorithms for this problem? This is actually an open problem in algorithms. So the best we know is that we can get an approximation factor of 2 minus something that converges to 0 when n goes to infinity. So essentially, we are just slightly better than 2. And that's the best we know. There is a lower bound. So unless p equals np, vertex cover cannot be approximated better than this factor in this factor 1.36. And that's, of course, very far away from 2. What we can say is that vertex cover cannot be approximated within a factor of 2 minus epsilon if the unique game conjecture holds. So this is a statement about assuming that a certain problem is NP hard to approximate. So assuming this, we cannot do better. Before I wrap up, let me make a short remark about matchings versus vertex covers. What we used is that the maximum matching is a lower bound for the minimum vertex cover. And we saw that we don't necessarily have equality here. The maximum matching does not need to be the same size as the minimum vertex cover. But there are classes of graphs where we have this equality, in particular in the case of bipartite graphs. So this is a well-known theorem. In bipartite graph, the size of the maximal matching equals the size of the minimal vertex cover. Meaning that for bipartite graph, min vertex cover and the max matching problem are the same. And this is interesting for the following reason. If you look at the complexity classes P and NP, and where you have matchings and where you have some max matchings and min vertex cover. So min vertex cover is an NP problem. So if P is not equal to NP, it's outside of P. But matching can be solved in polynomials up time, which means that in this particular case of bipartite graphs, minimum vertex covers can actually be computed in polynomial time, and the problem is for this specific class of graphs, not NP hard. Let me wrap up. The main result was that we can give a true approximation for the minimum cardinality vertex cover problem by simply taking a maximal matching, taking both vertices of each of the edges in the matching and using that set of vertices as vertex cover. Key ingredient was that we had a lower bound on the optimal value, so the minimum value for the vertex cover problem, namely the size of a matching. An important technique or tool in designing approximation algorithm is also to look at tight examples. This allows you to understand whether the approximation factor that you've seen so far is actually the approximation factor that the algorithm gives you. If you run into bottlenecks there, it also gives you an indication of how you need to change your algorithm to improve. This was, in our case, not possible because as long as the unique games conjecture holds, we cannot really get much better than the factor 2 that we've already seen.